So hi everyone, we are from Rivers Group. We are consist of Ahmad, Dewa, Aulia, Firdausi, Farelia, Octa, Viola, and Hilda Chairunnissa. So we would love to present our work on elementary linear algebra course, and we'll mainly discuss about the reduced LU factorization. So the content of this video is first the concept of reduced LU factorization. So it will be discussed by me, and the next one is the steps and examples of doing LU factorization will be discussed by Hilda, and the third one is the examples of its application and answer of a question, which will be discussed by Ahmad Dewa. And first of all is the concept of reduced LU factorization. So first of all, we need to know the definition of reduced LU factorization. In numerical analysis and linear algebra, lower, upper, and or LU decompositions or factorization factors a matrix as the product of a lower triangular matrix and an upper triangular matrix. A factorization of a matrix A is an equation that expresses A as a product of two or more matrices, whereas matrix multiplication involves a synthesis of data combining the effects of two or more linear transformations into a single matrix. In the language of computer science, the expressions of A as a product amounts to a pre-processing of the data in A, organizing that data into two or more parts whose structures are more useful in some way and potentially more accessible for computation. Before understanding how to construct L and U triangular matrices, we should look at why they are so useful. Why it is so helpful in the world of computer science. So M is equal to LU is called an LU decompositions of M. This is a useful trick for many computational reasons. It is much easier to compute the inverse of an upper or lower triangular matrix. So basically, LU factorization changes a complicated matrix into two significantly simpler matrices, which will bring us to more or easier to compute the inverse of an upper or lower triangular matrix. And the next one is the LU factorization. So we next consider a more general linear system AX is equal to B, for which we assume that there is a lower triangular matrix L and an upper triangular matrix U, such that A is equal to LU. So basically, like what we have said before, A is equal to LU, and then we just change the A becoming LU. And then such a system is more general since it clearly includes the spatial case of A and being either lower or upper triangular in order to solve such a system. We can again exploit triangularity in order to produce a solution without applying a single elementary row operation. So before we jump too far, we need to know the goal of doing LU factorization is to produce a solution without applying a single elementary row operation also. And to accomplish this, we first set y is equal to ux. So in that case, we bring together the u and x using the what we call the product of one of mathematics procedure, and then the y. So the y is equal to ux. So in here we know that where x is the as yet unknown solution of ax is equal to b. So then know that y must satisfy ly is equal to b, and then as L is a lower triangular, we can't solve for y via forward substitution, assuming that the diagonal entries of L are all non-zero. Then once we have y, we can apply back substitution to solve for x in the system. Since the U is upper triangular, as with L, we must also assume that every diagonal entry of U is a non-zero. So maybe that's all. The next part will be discussed by Hilda.
An example of how doing the LU factorization. So there are matrix A, L, and U. And the matrix L will be the product first vectors of the matrix A. And the matrix U will be the second vectors. Matrix L called as a unit lower triangular matrix. That means it's got one as a main diagonal of the matrix, and the lower part will entries with any real numbers. And the matrix U called as a unit upper triangular matrix. So it can have any real number entries on or above the diagonal of the matrix. So and to find the LU factorization, we use reduced row echelon. So we use reduced row to change the matrix A into matrix U, because like I said before, if U is an upper triangular matrix and have any real numbers on or above the diagonal matrix. And for the matrix L, we obtain from the coefficients of the reduced row which is conducted. So the next is the example of how do the LU factorization. So find the LU and use the LU factorization of A to solve AX equals to B, where B is the matrix of -9, 5, 7, and 11. So we start from the identity of matrix L. So this is the identity of matrix L, which that have 1 as the main diagonal of the matrix. So this is the matrix A. First, we reduce from the row 2 and row 3, and we get this matrix, and continue with reduce the row 4 and row 3, and the last is reduce the row 4, and we get the last result is the matrix U. So because the matrix U obtained from the reduced row echelon. And for the matrix L, we just need to write down the coefficients when we reduce row echelon, and we can verify to make sure that the LU is appropriate, like this. And the last, to find the solution of x, we use the LU factorization that we already doing before. And first, we need to solve the Ly equals to b to find the matrix y. To find the matrix y as follow in this slide. And to find the y, we need to use the reduced row echelon again to find the y, and we got that y is the matrix y is -9, -4, 5, and 1. And after we've got the matrix y, we can start to find the x. Use ux equals to y to find the x. So same like before, we use the reduced row echelon to find the x, and we get the result of x is 3, 4, -6, and -1. So the next part will be presented by Ahmad Dewa.
The next one is answering the questions with arguments. So, our group is choosing question number 22 about reduced LU factorization. Here's the question. With A as in the practice problem, find a 5x3 matrix B and a 3x4 matrix C such that A equals to BC. Generalize this idea to the case where A is mxn, A equals to LU, and U has only 3 non-zero rows. As you can see, the box below is matrix A from the practice problem. So let's get started. This is the LU factorization concept. The L matrix contains half of the matrix identity, which the other half is the thing that should be found. The U matrix is the inverse from the matrix L. Since the half diagonal contains 0, it needs to be found by finding the inverse coefficient from every reduced row that used to make the matrix A into matrix U form. But before we next, let's take a look for a while to the question. It's stated when A equals to BC, then A equals to LU. So it means BC equals to LU, then B equals to L, and C equals to U. Okay, this is the method that will be used. First of all, we need to assume the L and U as the goal. Then we need to transform the matrix A into the form of matrix L and U. Starting with create to table here. The left side is for the matrix U, which came from the matrix A. Then the right side is the matrix L, which is the identity matrix, but following the question, the matrix L or B, it contains 5 rows and 3 columns, so just follow that things, okay? Next, begin with finding the first pivot. This column is that we want to make it into matrix U form or the 0 section. Find the way for R2 becomes 0. We need to minus the R2 using 3 times of R1. As I said before, since the matrix L and U is inversing each other, so the zero maker coefficient in matrix U should be inversed before input it onto the matrix L. Putting the coefficient should follow this rule. Put it on the row that created to be 0 and in column of the zero maker. This one, the purple one, is the result after doing the equation in here, R2 minus 3 times of R1. Then put the coefficient of the 3 into the row 2 column 1 in matrix L. Why? Since it's the negation from this one, the coefficient in the matrix U. Next, making the row 3 column 1 in matrix U into 0. Subtract the R3 with R1. Again, the purple is the result. Then putting the coefficient 1 since R3 is already subtracted by R1. So minus 1 becomes 1 since it's the negation for this one. To the matrix L at row 3 column 1, this one. Next, Making the row for column 1 in matrix U into 0. Subtract the R4 with 2 times of R1. The purple is the result. Since the coefficient of 0 maker is -2, this one, then we should input the positive 2 into the matrix L at row 4, column 1. And then, the last for first pivot. Making the 5 row column 1 in matrix U into 0, this one. How? Add R5 with 3 times of R1. Since the coefficient of 0 maker is +3, then we should input the -3 into the row 5 column 1 at matrix L, since it's the negation from this one. Now it's done for the first pivot. The next one is second pivot. This is the second pivot, -4, -9, -7, -2, and 3. Okay. Then, starting with add the R3 with R2. Since the coefficient of 0 maker is +1, so we need to input the -1 at row 3 column 2 at matrix L, since it's the negation also. Next, subtract R4 with 2 times of R2. The coefficient of 0 maker is -2. Then +2 or the positive 2 is needed to put at the row 4 column 2 also, okay, at matrix L. The last one for second pivot, adding R5 with 3 times of R2. Since the 0 maker coefficient is +3, we need to input the negation of it, which is -3 at row 5 column 2 in matrix L. Then it's done for the second pivot. Next is the last pivot, third pivot. Since the question is only asking for the matrix L with 5 rows and 3 columns, this is the third pivot, -2, -5, 3, -2, and 3. And then how to make it into the 0? Yeah, this is the way. By adding the R4 with R3, since the coefficient in here is plus, then we need to put the negation of this one, which is the -1 at row 4 column 3 in the matrix L. And then the last, making the 0 for the R5. How? By subtracting the R5 with the 2 times of R3. Since the coefficient in here is -2, so we have to put the negation of -2 in the matrix L, which is 2 at row 4 column 3. Okay, and then it's done. Here's the result. Matrix U or C, which has 3 rows and 4 columns, and the matrix L or B, which has 5 rows and 3 columns. For proving, trying to multiply the matrix L with matrix U. If the result is A, so it's correct. Here's the proof using the online calculator, and it's proof. This is the result, yeah, from the online calculator. Thank you.